Hello everyone, I'm Zhenbo Hu from Harbin Institute of Technology, Shenzhen. Today I'm going to present our paper, Delta-DNN, efficiently compressing deep neural network via exploiting flaw similarity. This is the outline of my presentation. First, let me introduce about neural networks. Deep neural networks are designed to solve complicated and nonlinear problems. There are many related applications. Two typical applications are computer vision and natural language processing. Why we need compressed neural networks? To further improve the inference accuracy, DNNs are becoming deeper and more complicated. Meanwhile, the frequent training of DNN results in huge overheads of storage and network. The overhead overwhelms resource-constrained platforms such as mobile devices and IoT devices. For instance, a typical application is to train a DNN in the cloud servers with high-performance accelerators, such as GPUs and TPUs, and then transfer the trained DNN model to the edge devices to provide intelligent and effective service, while the cloud to edge data transfer is very costly. Compressing neural networks is an effective way to reduce the data transfer cost. However, existing approaches focus on two ways, include traditional data compression and model compression. About the traditional data compression techniques, they are especially important for data reduction. Generally, data compression can be categorized into lossless compression and lossy compression. Lossless compression has been developed for decades. They usually deal with data as byte streams and reduce data as byte or string level based on classical algorithms such as Huffman coding, dictionary coding. Some special lossless compression, such as dirt compression, it observes the high data similarity and thus the high data redundancy in the neighboring versions of fields in backup storage systems, and then records the dirt data of neighboring fields for space saving. Lossy compression appears for decades too. The typical lossy compressors are designed for images. Nowadays, more attention is paid to the lossy compression of floating point data generated from HPC. Focused on SC, it is designed for scientific data to get a high compression ratio by exploiting the characteristics of floating point numbers. Specifically, there is a date beating predictor in SC's workflow. The predictor outlines the characteristics in flows for prediction while ensuring the point-wise error controls on demand. Recently, with the rise of AI boom, efficiently compression DNNs are gaining increasing attention. However, due to the DNNs consist of a large amount of random floating point numbers, they are not easy to compress. The existing traditional data compression approaches only achieve a very limited compression ratio on DNNs. Therefore, other special technologies are proposed, such as pruning and quantization. Pruning is focused to remove some unimportant parameters of a DNN, like the subfigure on the left. Quantization is focused to transform the float parameters to low-bit numbers, like the subfigures on the right. As introduced before, there are many float point parameters in a DNN, and in the training process, some parameters vary greatly, while some parameters vary slightly. So we collect 100 versions of 6 popular DNNs in training, and then linearly fit out the corresponding parameters from every 2 neighboring networks as this figure. Besides, we use a metric called structural similarity, SSIM, that's widely used to measure the similarity of two metrics like DNN's parameters. Also shows in this figure. We can observe that the results of the linear fitting are very close to y equals x, and the values of SSIM are very close to 1. So we believe that the floating point numbers of neighboring networks are very similar. Therefore, according to our observation, we present our motivation of this paper. First, inspired by the dirt compression technique used in the area of backup storage, we calculate the dirt date of the similar flaws between the two neighboring neural networks. Second, we employ the ideas of error-bound LZ lossy compression that are a date-fitting predictor and an error-controlled quantizator to compress the dirt date while ensuring the inference accuracy loss under control. The general workflow of the DNN framework is shown in this figure. To compress a neural network, we call it target network. We need a reference neural network. A reference neural network is usually the former version of this DNN in training process. Specifically, the DNN consists of 3 key steps. First, calculating the dirt date is to calculate the lossy dirt date of the target network and the reference network. Second, optimizing the error bound is to select the suitable error bound used for maximizing the lossy compression efficiency. Third, compressing the dirt date is to reduce the dirt date size by using lossless compressors. About the first step, calculating the dirt date, we follow the idea of SA lossy compressor. Specifically, we denote a parameter from the target network as AI, and the corresponding parameter from the reference network as BI. And the lossy dirt date of flows AI and BI can be calculated and counted to MI as the first formula. This step, we convert float point numbers to integer, and according to the date similarity we observed, that most integers are equal to 0. That means they are highly compressible. And with the dirt date MI and the reference network parameter BI, we can easily recover the target network parameter AI as illustrated in second equation with a limited loss based on the error bound. How to get a reasonable relative error bound to maximize the compression ratio of the DNN without compromising DNN's inference accuracy. We know that the larger error bound results in the smaller conjugation factor, and thus the higher compression ratio. At the same time, it leads to an uncertain inference accuracy loss of DNNs. This figure shows that the impact of inference accuracy with different error bounds. This phenomenon is because the recovered target network parameters would vary randomly with different error bounds, sometimes larger, sometimes smaller. This figure shows the impact of compression ratio with different error bounds. Therefore, in DNN's workflow, we need to find a reasonable error bound for both considering two key metrics, the compression ratio and the inference accuracy loss. Our solution is selecting an optimal error bound by assessing its impact on both compression radio and inference accuracy loss. Generally, it consists of two steps. First, collecting the results of compression radio and the inference accuracy degradation, along with the available error bounds, while meeting the requirements of the maximal total accuracy loss of the tested DNN. Second, assessing the collected results to select an optimal error bound according to this formula. Phi is the relative loss of inference accuracy. It calculates the recovered network after decompression and compare it with the original network. Omega is the compression radio. The radio is the radio of the fuel sets before compression times the fuel sets after compression. Alpha and beta are the influencing weights defined by users. They are used to fine-tune the importance of phi and omega. So we can use the score to assess the compression efficiency to select the optimal error bound and satisfying users' requirements on both the compression radio and the inference accuracy. The last step is compressing the third date. In the first two steps, we have calculating the lossy third date with the optimized error bound. For further compressing the third date, we use the lossless compressor to compress the integers. Considering the third date are calculated from the very similar flows, we test some combinations of G-standard, LJMA, and run-length encoding lossless compressor. As the figure shows in the right, we find that the hybrid approach combining run-length encoding and LJMA achieves the highest compression value on all 6 DNNs. Thus, we adopt this hybrid approach to compress the lossy third date into the compressed binary field. Here we introduce two typical application scenarios for third compressing DNNs use Delta-DNN. First is optimizing network transmission for DNNs. We consider a popular way that DNNs are trained on the server and deployed locally on the client, like mobile device and IoT device. Therefore, the process of transferring the newly trained model from the server to client is usually similar to the software updating on the smart device. In this scenario, the network of the resource-constrained class is usually a system bottleneck when updating DNNs. Thus, applying the DNN in this scenario, just as this figure, can optimize the network transmission for DNNs by compression. Here is the second scenario, using the DNN to save storage space for DNNs. In many applications, neural networks need to be trained with dynamically growing datasets, like transfer learning and incremental learning. In these situations, multiple snapshots or versions of DNNs need to be saved in the training process. That may occupy lots of storage space. In this scenario with DNN, we can only save the original version of DNN fully, and the follow versions will be saved as a lossy third date. This is much smaller than a full version. Thus, the storage space can be greatly reduced, as shown in this figure. Here I will introduce about performance evaluation. These are the related information of our experimental setup. Here are the results of the compression performance of DNN. We compare our method with the state-of-the-art approaches, LZMA, G-standard, and SD. According to this table, we can easily find that DNN achieves about 2 times to 10 times higher than others, and DNN can keep the inference accuracy loss smaller than 0.2% as the default setting. Here are the results of case 1, optimizing network transmission. We consider the network configuration for this case is including the upload of fixed broadband, download of mobile broadband, and fixed broadband. The network bandwidth state is from the speed test net in January 2020. As this subfigure showed, the test cost of network transmission of 6 DNNs. It can be seen that DNN significantly reduced the network consumption. This is because DNN compressed DNNs about 10 times smaller than other ways. About the case 2, saving storage space. We compare DNN with other compressors on 2 metrics, the DNN's inference accuracy and the storage space overhead. As the table shows, DNN can efficiently reduce the storage size of 6 DNNs by 5 times, while the average inference accuracy loss is very low. And this figure shows the comparison of inference accuracy using DNN or not when training DNNs. We can see that we can see whether using DNN or not, the inference accuracy is almost the same. Here is the conclusion and future work. In this paper, we propose a novel third compression framework for DNNs called Delta-DNN. It can significantly reduce the size of DNNs by exploiting the flow similarity existing in neighboring networks in training. And according to our evaluation, DNN achieves 2 times to 10 times higher compared with G-standard, LZMA, and ASIC approaches. Also, we control the inference accuracy loss always smaller than 0.2%. In our future work, we plan to further evaluate our DNN on more neural networks and more datasets. And we plan to further improve the compression ratio by combining other model compression techniques. Furthermore, we will continue to extend the DNN into more scenarios. That's all for this presentation. Thank you.